whatever. But yeah, let's just remember that gravitational potential energy, the formula for that is mass times gravity times height. Make sure to you do answer these polls. I am going to use one of these polls as attendance. And I'm going to use one of these polls as attendance. Ten results. Yeah, guys, it's fine if you don't know. Make sure to answer, guys. Make sure to answer. I'm going to go over it in like 30 seconds. Zero because that doesn't have height. Good. It starts from zero. It starts from zero and it decreases. You can't go below the ground. I'm assuming that's a typo. Yeah, but there is no potential energy because relative to the ground, the height is zero. Yeah, exactly. I like this one the most, right? Relative to the ground, the potential energy starts at zero because its height is zero. You don't have any potential energy, guys. Thinking about it this way. When do you make more sound? What if you were to drop your entire your laptop right now? Actually, your phone. What would make more sound when it hits the bottom? Your phone, when you drop it at a very low height, versus dropping your phone from a height of 1 meter. In which situation is something going to make more sound? Or in which situation would something be more deformed? Right? So if you drop something at a higher height, it's going to make more sound when it hits the bottom. Where does that energy come from? That energy comes from the increased potential energy that you have due to gravity. Guys, there's a perfect I'm not perfect transfer, but there is transfers of energies here. If you're at a higher height, you have a higher gravitational potential energy, which is basically in the formula, guys. Question is confusing. Don't know. This is very worrisome. This is very worrisome mainly because in 5.3, we did questions on this. As a student walks downhill at constant speed, his gravitational potential energy does what? Decreases. Why does it decrease? Because your height decreases. Number 7, as car travels at a constant speed up a hill, what happens to your gravitational potential energy? Your gravitational potential increases. Why does it increase? Because your height increases. It's in the formula, guys. If your height is zero, you don't have any gravitational potential energy. This is very worrisome, right? This is very worrisome because we've been dealing with gravitational potential energy since lesson 5.3. If you're still struggling with this formula, you really do need to step it up, right? If your height is 0, everything else is 0. You don't have any potential energy. You have nothing to do. Again, a reminder, guys, any one of these polls I can take as attendance. Does the barbell gain potential energy after he lifts it? And how do you know? This should be very clear from the previous question. I'll explain the previous question. Should be very clear. Is it possible to have negative PE? Negative energy means you're taking it away from the system. Basically means you're losing that energy. But technically, it's pretty impossible to have a negative PE. Because sure, yes, but in in it in reality, no. It's possible, but in reality, you're never gonna come across the situation whereas you're gonna have negative PE. Guys, I'm gonna give you one more minute. I'm gonna give you one more minute to come up with an answer, guys. Again, any one of these attendance polls I can and will use as attendance. You guys have 45 seconds. Do this. God damn it. Possible to have a negative. Okay, I already read that question. Guys, I already locked the poll. Turns out this was your attendance question. You're about to hit enter on your keyboard. Oh yeah. Okay. I'll mark it here, guys. Do you guys on your end, do you see a timer? I just want to make sure. You guys do see a timer on, you don't see a timer on your end. Okay, that makes sense. Yeah, so there's a barbell gain potential energy. Yes, yes, yes. Yes, there's a change in height. Yes, there's a change in height. Yes, height changes. Good. Right? Because your potential energy changes, right? The formula for potential energy is mgh. If your height increases, you're gaining potential energy. Gravity can do work on this barbell now. If you were to suddenly let go of the barbell, gravity will do work. Right? Your height increases after you lift it. So, which brings us to what we're going to be learning about today, which is called the work energy theorem. So, we've learned a couple of formulas so far. We learned these two. We learned those two on Monday and Tuesday. We've learned about these two on lesson 5.3, right? We've learned about power. We've learned about the conservation of energy. We've learned about work. And the final thing we need to learn about is the relationship between work and delta ET. That is what we need to learn about. So what is this, right? This is called the work energy theorem, and it's one of the most important concepts in physics. Right? This is one of the most important concepts in physics. Work is equal to delta ET. Well, let's talk about what that is. Right? What is delta ET? And before we start, what's delta V?
Change in velocity.
Change in velocity. And what is that in formula format?
Time over distance.
Distance, that's V average, right? That's distance over time. Your average velocity is distance over time. But what's your change in velocity? How do we calculate the change in something? My initial, I started with a velocity of 10 meters per second. After 5 seconds, my velocity is now 20 meters per second. What is my change in velocity? Who is your math teacher? Who are your math teachers, guys? Oh my God. All right. Guys, think about it this way. You have $2. The next day, you have $7. What is the change in money amount that you have? 5. How did you get 5? What did you do? 7 minus 2. So if you apply that to change in velocity, what's my change in velocity? What's the formula? VF minus VI. Good. Your final velocity minus your initial velocity, which is your change in velocity. Right. So we apply this this concept to delta ET, which is basically your final energy minus your initial energy. And if we were to break this down, right, we were to break this down, I'm actually going to break it down for you because it's basically your change in potential energy plus your change in kinetic energy. Remember, total energy is PE plus KE plus Q. For the most part, we're just not even going to talk about Q, guys. We're not even going to talk about Q. So we're just going to ignore that part. So this is where the delta comes from, right? If your total energy is equal to all your individual energies, then well, your delta ET is equal to delta PE plus delta KE. And this becomes final potential energy minus initial potential energy plus final kinetic energy minus initial kinetic energy, which is this. Now, here's the important thing, right? Work energy theorem is extremely important. And it's basically saying that, well, if you do work on an object, we change the total energy that the object has. If someone pushes you, they're doing work on you. Or rather, if you do move a distance, they are doing work on you. If you throw a ball, you do work on that ball. If you are writing something down, you are doing work on the pencil or the pen or whatever utensil you use. So basically, if you're applying a force over a distance, you're doing work on something. And when you do work on something, you change the energy that the object has. Take, for example, this guy, this deadlifter right here. He is doing work on this deadlift. I mean, not deadlift, on this barbell. He's giving the barbell potential energy. He gave the barbell potential energy by doing work on the barbell. So now the barbell has potential energy. And when he lets go of the barbell falls. That potential energy turns into kinetic energy. And then once it hits the ground, bounces a few times, it loses all that energy due to heat. Tell me, who is doing the work here? And how does that work? Or rather, what is the type of energy that is being increased here? Of which object? Well, let's start with who is doing the work in the first GIF. Yeah, nice.
Has to be the person because he's lifting.
We're talking about the car, right? We're talking about the GIF on the top.
Oh, no, I
The
wasn't
one I
paying
circled?
attention.
Yeah. I mean, you're right. The person is lifting the barbell, so he's doing work. But the person on the top is also doing work on the car, right? So the person is doing the work on the car. And work, guys, again, to remind you, work is measured in joules. You're expending energy. This guy who is pushing this car is expending energy. Where does that energy go?
Into the car.
Into the car, and the car gains something.
Kinetic energy.
Yes. You did work on this car and the car gains kinetic energy. This guy expended energy and that energy got transferred into the car's kinetic energy. Where does the man's energy come from? Comes from the food he eats, right? The energy between atoms and bonds. And your body breaks them down into ATP. It's a very simplified process of it, but maybe you learned in living environment. What about this GIF? This GIF is a little bit harder. I'll be impressed if you tell me who or what is doing the work on this car. Clearly, my energy changes, guys. What energy am I losing?
Kinetic?
You're losing kinetic energy. The car stops. Work must be done for this car to lose energy. What is doing the work? Like I said, I'll be pleasantly surprised. I need a stretch. I need a stretch. Yeah, okay. So whoever probably messaged me, both of you are correct about the sources of the work, but what is the work being done? It's a very specific term. I'm gonna go stretch.
So directly being stopped because it's colliding with the two cars.
All right. All right, guys. This is a
Energy
specific
friction?
term. Friction. Wait, did you say kinetic friction?
No, just friction.
Okay, friction. Yeah. Friction is slowing this down. So there's work being done by friction. Friction applies a force over a distance and is doing work. You guys might not realize it, but the fact that these two surfaces even connect, that's friction. It doesn't have to be tires above cement to count as friction. As long as you have two surfaces contacting, that counts as friction. That counts as friction, guys. So didn't want to go too far. But yeah. So this is a very important concept, guys. By doing work, we change the energy an object has. Very important concept. All right, well, we have 4 practice problems to do tomorrow. We do have 4 practice problems. But we're gonna watch this video.
Work means a lot of things to a lot of people. In physics, work has a specific meaning. Work equals force times displacement. I'm using my force to move this cell phone across the table. That's work. Moving a product to market is work. Moving a rocket into space is work too. How much energy do you need to propel that rocket into space? How much gas, which possesses stored chemical energy, do you need to drive across the United States in your car? Or how much energy do you need to keep this manufacturing plant assembly line in operation? That's what the work energy theorem helps you figure out. It took about 2,000 years to figure out that forces are what make objects move and stop. When I roll this ball on the table, do you think it'll stop? Greek philosopher Aristotle did. In Aristotle's days around 320 BC, he thought objects would just naturally slow down and stop. It wasn't until Sir Isaac Newton came along almost 2,000 years later that he figured out that forces like friction that are harder to see and measure are acting on the ball and slowing it down, or other forces speeding it up. It's Newton's first law of motion. An object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by a net force. So without friction, this ball would just keep on rolling. Newton understood forces acting on masses, but he didn't really take into account energy's impact on how things move. That took years more to figure out. And in the world we're living in, with industry and technology, energy is critical. The key to the work energy theorem is understanding that the work you do on an object will either add energy to that object or take energy away. Remember, work equals force times displacement. So let's say I want to move this box 2 meters. If I exert 20 newtons of force on the box to move it 2 meters, then I'm doing 40 joules of work on the box. By pushing the box and increasing its velocity, the box gains 40 joules of kinetic energy. Kinetic energy is the energy of a moving object. That's the
If you roll a ball, wouldn't it stop at some time? Yeah. If you were to roll a ball, it would stop. How is it going to stay in motion? Newton's first law says an object will stay at constant velocity or will stay at rest unless acted on by an external force. On Earth, if you roll a ball, friction stops you, right? Friction is the force that slows you down. If friction wasn't available, or rather, if friction didn't exist at all, the object would continue to go and go and go. Right? If you think about something in space, while there is friction in space, there are vast amounts of, or rather, there are particles in space, but they're all really just spread out. You do experience very, 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 very low amounts of friction in space, but barely any. Which is why you can see that spaceships, or rather not spaceships, but satellites go at extremely high speeds. Actually, what is the speed of Voyager 1? "17 kilometers per second." It's already outside of the solar system. 17 kilometers. Equivalent. What is 17 kilometers? I don't care about the miles. I don't care about these measurements. Okay, let's think about like 1 kilometer is like a football field, guys. So think about the satellite traveling 17 football fields per second. That's the speed of Voyager 1 exiting our solar system. Voyager 2 is traveling at 19 kilometers per second. Why can it reach that speed? Because there's barely any friction in space.
the work energy theorem in a nutshell. Work is equal to the change in that object's kinetic energy. Kinetic energy is equal to 1/2 your mass times its.
So how work energy theorem is usually taught. Work energy theorem is usually taught as work is delta KE, which is how I learned it. Well, on the New York State regions, the work energy theorem is taught as work is equal to delta ET. Why? You'll realize that as we go on through practice problems that these two don't really make a difference. It doesn't make a difference which one you use. And I'll explain as the video goes on.
Velocity squared. The delta symbol means a change in. That means work is equal to the final kinetic energy minus the initial kinetic energy. The key is it has to be displaced. If you move it, then return it to the same spot, no work is done. Why are forces like friction important? Well, if you want to know how much friction slows down a runner sliding into base, or how big a parachute you need to slow down this shuttle, or how fast a train can safely take a curve without flying off the tracks, the work energy theorem can help you figure out these problems. And in each of those instances, friction is a key force. Friction is one of those forces that's difficult to measure. It takes away from kinetic energy. In the case of someone sliding into base, it takes kinetic energy and turns it into heat. The same way when you rub your hands together real fast, you can feel the heat. You can calculate the energy lost due to friction in problems by using physics that we've already learned. How much work does friction do if an 85 kilogram base runner travels at an initial velocity of 8 meters per second and slides into second base and then stops?
Give me my notes. We're gonna do this problem together. Notes, let's go. Okay. Knowns, guys? Come on. Hello?
Velocity is 8 meters a second.
Yeah, velocity, initial velocity is 8 meters per second. Mass is 85 kg. There's one more known, and something else we need to solve for? Work, you're solving for work, yeah. One other known. Yeah, VF is 0. Final velocity is 0. And so you're gonna approach this problem by using the work energy theorem. Friction is doing work on this baseball runner. Delta ET is equal to delta PE plus delta KE. Is there a change in potential energy here? If my initial height is 0, if I start at first base and I end at second base, is there a change in potential energy? Should be quick, guys. My confidence in your understanding of potential energy is lacking now. The guy starts at first base. The guy ends at second base. I'm assuming baseball bases don't end up on a hill. Like you're not going up a hill, you're not going down a hill to go through these bases. Actually, I think I'm assuming something terrible because some of you might not even know how to play baseball, which is my fault, right? I'm sorry, actually. So there are 4 bases in baseball, right? And they're all basically on the same height. Relative to the ground, they're basically all at the same height. So is there a change in potential energy if your height is 0? No, there's no change in potential energy. So your change in kinetic energy is Ke final minus Ke initial. Work is equal to 1/2 mv squared minus 1/2 mvi squared. We're gonna finish the rest of this video and then you guys can go. There's like only 1 more minute left anyway.
So let's write down our knowns and our unknowns. Mass is equal to 85 kilograms. Our initial velocity is 8 meters per second. Our final velocity is 0 meters per second. And we're solving for the work done by friction. And here's the equation that we need to know. Work is equal to the final kinetic energy minus the initial kinetic energy. That means that work is equal to 1/2 the mass times the final velocity squared minus 1/2 mass times
Just bear
the
with it,
initial
guys. It's like
velocity
1 more
squared.
minute. All
We're going to
right.
plug in the values we know.
Leaving 1 more
Work
minute
for
early
friction is
doesn't
equal
make
to
a
1/2
difference.
times 85 kilograms times 0 meters per second squared minus 1/2 times 85 kilograms times 8 meters per second squared. Now the first part of the equation will be equal to 0 since 0 times anything is 0. And that leaves us with 1/2 times 85 kilograms times 8 meters per second squared. When we multiply that out, we get the work done by friction to be negative 2,720 joules. So friction takes energy away from the kinetic energy of the base runner, right?
which is
are we
why the work
getting-
is negative, right? Energy is being taken away, which is why work here is negative. Friction takes away energy from the baseball runner. Guys, we'll do more practice problems tomorrow, all right? See you guys tomorrow.